Hello everyone. Today in this video, let us discuss all these sums from 1 to 7 from exercise 1.2, which are based on theorem 1.2, fundamental theorem of arithmetic, which we have learnt already in the previous video. Okay, so let's start. Coming to the first question. Express each number as a product of its prime factors. Okay, in that the first question is 140. So we need to do prime factorization of 140. Let's do. Start with 140, divide them using only prime numbers. Remember the prime numbers are, I'll write here, 2, 3, 5, 7, 11, 13, 17, 19, 23 and so on. Don't use any other numbers. Please divide only with the prime numbers because this is a prime factorization. You need to divide with only the prime numbers. So any table out of these you can use. So let's start with 2. 2 table goes in 140. So 2 7s are, 2 zeros are, 2 70s is 140. Again take 2 table, 2 35s are 70. Next again let us take 5 table, 5 7s are 35. Next 7 1s are 7. Right, done. So 140 can be written as, write all these numbers, 2 into 2 into 5 into 7. This is the prime factorization of 140, which you can write as, if you have repeated prime numbers, you can write them as powers of prime, 2 square times 5 times 7. This is your 140 prime factorization. Let us do for 156. 156, let's divide with only prime numbers. Let us take 2 table first. 2 7s are 14, 1 remainder 16, 2 8s are 16. Next, again we can take 2 table. 2 3s are 6 is the nearest, 1 remainder 18, 2 9s are 18. Next, let us take 3 table. 3 1s are, 3 3s are. Next, 13 is a prime number. So, you can take 13 1s are 13. So, done. The prime factorization of 156 is 2 into 2 into 3 into 13. Which you can write as 2 square times 3 times 13. Okay, let's go to the next one. 3825. 3825. Let's do the prime factorization for this. Because at the end number is 5, we can take 5 table. So 5 table, 5 7s are 35, 3 remainder 32, 5 6 are 30, 2 remainder 25, 5 5s are 25. Next again take 5 table. 5 1s are 5, 2 remainder 26, 5 5s are 25, 1 remainder, 5 3s are 15, 153. Let us divide now with the 3 table. 3 5s are 15, 3 1s are 3. Next again divide with 3 table. 3 table will get 3 1s are 3, 2 remainder, 3 7s are 21. So 17. 17 is a prime number. We can continue. 17 1s are down. So 3825 can be written as 5 times, I'll write down 5 times 5 times 3 times 3 times 17. So you can also write in a ascending order and powers of prime. 3 is repeated 2 times, 3 square, 5 is repeated 2 times, 5 square. I'm writing in increasing order into 17. That's it. Next, write one more. Fourth question, 5005. Let us take 5005. Let us divide with 5 table as it is having last digit 5. Anytime, whenever you have last digit as 5, you can start with 5 table as 5 is also prime number. So let's start with 5 table. 5 1s are, 0s are, 0s are, 5 1s are. 1001. You can take 11 table. 11 table, 11 9s are 99, 1 remainder, 11 1s are 91. Now take 7 table. 7 table, 7 13s is 91. Next, 13 1s are. So done. 5005 can be written as 5 into 11 into 7 into 13. If we write in increasing order, you can write it as 5 into 7 into 11 into 13. This is the prime factorization of 5005. Generally, we prefer to write ascending order. In whatever tables you may take in the beginning, finally write your answer in the ascending order. So it will be unique answer for with everybody. right? So now let us do with 7429. Let's move it little bit. Our next number is 7429. Let's divide this. Let's go to directly 17 table, because 2 table, 3 table, 5 table, 7 table, any table doesn't work until 17. So let's take 17 table. 17 437s are. Next, let us take 19 table. 19 table, we will get 19 twos, 19 threes, 23s are. Next, 23 table directly, because 23 is a prime number, 23 ones are. So 7429 can be written as, it has only 3 prime factors. 17 into 19 into 23. That's it. No prime number is repeating, just this is only the prime factorization of, and it is also in increasing order. So it is the prime factorization of 7429. Let's go to the second question. Let us see the second question. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of the two numbers. We have a relation that LCM into HCF is product of the two numbers. Let us verify that with these numbers. So let us see the first question. We have to find HCF. First let us find HCF of 26 and 91. Afterwards we find LCM of these two numbers. Let us use prime factorization for finding HCF. Let us take 26 and do the prime factorization. Let us take 2 table. 2 13s are, and 13 is a prime number, so 13 ones are, right? So 26 is equal to 2 times 13. Now let us take 91 and do the prime factorization. Let us take 13 table. 13 sevens are, and 7 is a prime number, so 7 ones are. So 91 is equal to 13 times 7 or 7 times 13. Always I prefer to write in ascending order. So now HCF is the common factor out of these two, which is 13 itself, only the 13. So HCF is 13. Now let us find LCM of these two same numbers. Let us use shortcut method, short division method otherwise we call. So let us take two numbers at a time and take a common factor for divisible by these two numbers. Let us take 13 is the table which divides both 13 twos and 13 sevens. As 2 and 7 are prime numbers and they don't go in any same table, we can stop doing division, or you can continue with 1 time 2 and 1 time with 7. Anyhow, you will get the same numbers to find out the LCM. So LCM is the product of 13 times 2 times 7, which is 13 into 2 into 7 is 182. Now let us take the product of HCF and LCM. So let us find HCF into LCM. 13 times 182, which is, if you do in your calculation, you will get 2366. And let's also find the product of the numbers and check whether it is same as this or not. Is equal to, the numbers are 26 and 91, right? Let us multiply these two. The answer is again 2366. So we verified that product of two numbers is same as HCF into LCM, or product of HCF into LCM is same as product of the two numbers. Let's go to the second point. Now let us see the second question in this. 510 and 92. So let's find out HCF of these two numbers first by using as usual prime factorization method. So 510 I'll take and prime factorize it. As the last digit is 0, I'll take 5 table. 5 table, 5 tens are 50, 1 reminder, 5 twos are 10. Next I'll take 2 table, 2 fives are 10, 2 ones are 2. Next I'll take 3 table, 3 17s are. And 17 is a prime number, continue, 17 ones are. So we got 1. So 510 is equal to 5 into, okay, I'll write in ascending order, 2 into 3 into 5 into 70. Okay, next coming to 91, do the prime factorization for 91. Let's take 2 table, 246 are. Next 2 table again, 223s are. 23 is a prime number. Let's take 23 table itself. 23 ones are. So write 91 is equal to 2 into 2 into 23. Now the common number in both prime factorizations, product of those numbers. Only one number is common. So no other numbers are common in the remaining leftover numbers. So just 2 is your HCF. Next, coming to finding the LCM of these two numbers, let us take as usual shortcut division method. We call short division method. 510 with 92. At a time we'll take both and take the common divisor of these two. Let us take 2 table only is divisible by both. So 2 table 255 are, 2 table 246 are. So that's it. So these two numbers will not come in any same table. You can leave it here and find out HCF is equal to 2 into 255 into 46. Sorry, LCM is equal to, LCM is equal to 2 into 255 into 46, which is equal to 23,460. Now let's find the product of HCF and LCM. HCF into LCM is equal to, HCF we got 2 into LCM is 23,460, which is equal to 46,920. So this is the product of HCF and LCM. Now let's find the product of the two numbers also. Product of two numbers. What are the two numbers? 510 into 92. So let's find the product of these two, which is also same as 46,920. If you do calculation, you'll get the same number. So we verified that product of HCF into LCM is same as product of the two numbers. Thus verified. Now let's go to third question in this. Now let's see the third question. 336 and 54. Let us find HCF of these two by taking prime factorization for both. 336. Let us take 2 table first. 2 table where you will get 2 ones are 2. 1 remainder 13. 2 6 are 12. Again 1 remainder 16. 2 8s are. So let us take again 2 table. 2 8s are 16. 2 4s are 8. 84. Let's continue. 2 table. 2 4s are 2 2s are. Let's continue. 2 table. 2 21s are. 3 table now. 3 7s are. And next comes 7 table. 7 is a prime number, so you can take 7 ones are. So 336 is equal to, let's write here, 2 into 2 into 2 into 2 into 3 into 7. Next, let's find 54, prime factorization. 2 table, 2 2s are 4, 1 remainder, 2 7s are 14. Next, 3 table, 3 9s are 27. Again take 3 table. Always use prime numbers only. Next, 3 ones are. So 54 is equal to, I'll write on the top, 54 is equal to, we have 2 into 3 into 3 into 3. So let's find out the common factors. 2 is common in both and 3 is common in both. So 2 into 3. So our HCF is the product of the two common factors, 2 into 3, which is 6. So our HCF is 6. Now let's find LCM of these two numbers by using short division method again. 510, sorry, we are doing third bit, right? 336 comma 54. Let's do the common table is 2 table where you will get 168 are, 2 table 227 are. These two comes in 3 table again, 356 are, 3 9s are, and 56 and 9 doesn't come in any same table. You need not factorize them. So you can stop there and find out the LCM is equal to 2 into 3 into the leftover numbers also you need to multiply, 56 into 9. So the final LCM of these numbers is, a product of these numbers is 3024. Now let's find the product of HCF and LCM. HCF times LCM is equal to 6 into 3024, which is equal to 18,144. So this is the product of these two numbers. Now let us find the product of the numbers what we have taken. Product of the numbers is equal to these two numbers product. 336 into 54. If you do calculation, you will get the same answer as this, 18,144, which is same as our HCF into LCM. So we verified the product of HCF and LCM is same as always the product of the two numbers what we have taken. Right? We'll go to next question number 3. Now let's see the third question. Find the LCM and HCF of the following integers by applying the prime factorization method. In that, the first question is 12, 15, 21. Let's see the first question. 12, 15 and 21. So let us do prime factorization method only. We have to apply only prime factorization method. So the prime factors, the 12 can be expressed as the product of primes as 2 into 2, 4, 4 into 3. So these are the prime numbers, 2, 2, 3. So 2 into 2 into 3 is 12. And 15 is divisible by 3. 3 into 5 is 15. 21 is divisible by 3. 3 sevens are 21. So these are all our prime numbers only. So we can write HCF is equal to, so the common factors, let's circle the common factors in each. 3 is common in all. So our HCF is 3. Only 3 is common. So now how to find LCM using prime factorization method? Along with the common factor which is the common in all, take it as one time, and the remaining which are uncommon, not common, they all comes here. You have to multiply all the numbers together. The common factor one time and the remaining all leftover numbers. Product of all these numbers comes to LCM. So 3 2s are 6, 6 2s are 12, 12 5 is 60, 67s are 420. So LCM is 420, HCF is 3. Let's go to question 2. 17, 23 and 29. So if you observe, these are all prime numbers, right? So 17 can be written as 1 into 17 because they don't have any other common factors other than 1 and itself. So 23 is also a prime number. So 1 into 23. 29 is equal to 1 into 29. So every number is a prime number. So except 1, they don't have any other common factor. So HCF will be 1. Next, coming to LCM. How to write LCM? So here common factor is 1. Other than 1, what are the leftover numbers? 1 into the remaining all leftover numbers, 17 into 23 into 29. Along with the common factor, we need to take the remaining common and uncommon factors also. So the product, that is nothing but the product of all the numbers itself. If they don't have any number common, you have to simply multiply the numbers itself. 1 into something gives you the same. So you need not consider this. 1 can be ignored. So the LCM of the numbers which don't have any numbers in common, we can call them as co-primes also. They don't have any number in common. So which has HCF is 1. So those numbers product only comes as the LCM. The product of these numbers is equal to 11,339. This is the LCM, 11,339. Now coming to question number 3. 8, 9, 25. Let's write the prime factorization of each number. 8 is equal to 2 into 2 into 2. 2 cubed. And next 9 is equal to 3 into 3. 3 squared. You can also write it as 2 cubed. And this you can write as 3 square. And next 25, which can be written as 5 into 5, which is 5 squared. So now here HCF is there any factor common in all? All 2's, all 3's, all 5's, all are different factors. You don't have any number in common. So if they don't have any number in common, you just think it as 1 is there common in all. So you can think 1 is the common factor for all. So 1 is the HCF itself. So the number which is common is 1 and the HCF is also the same 1. If they don't have any number in common, that means 1 is the common factor. So HCF is 1. Let's find LCM. Here also, other than 1, you don't find any numbers in common, right? So 1 into remaining all numbers. So 2 cube into 3 square into 5 square, which is equal to, that is nothing but 8 into 9 into 25, which is same as the product of the same numbers itself. If they don't have any number in common, LCM will be the product of the same numbers. So 8, 9, 72, 72 into 25 multiply, you will get 1800. So this is the LCM of these three numbers. Let's go to the question number 4 now. Let us see the question number 4. Given that HCF of 306 and 657 is 9, find LCM of 306 and 657, the same numbers. He has given HCF of the two numbers, which is 9, and he is asking LCM of those same two numbers. Okay, so how to find LCM when HCF is given? We know that the relation between HCF and LCM as HCF into LCM is equal to product of two numbers. Use this relation. So we know HCF is 9. 9 into LCM is equal to, what are the numbers? 306, the product we are taking, into 657. So now we need to find LCM. LCM is equal to, send 9 to the other side, which gives you 306 into 657 by 9. Okay, let's cancel. So 9 table, 9 ones are 9 table 306. First 30 we'll see. 9 4s, 9 3s are 27. 3 remainder 36. 9 4s are 36. So our number LCM is equal to 34 into 657, which is equal to 22,338. So this is the LCM of those two numbers. Therefore, LCM of 306 and 657 is equal to 22,338. Now let's see the question number 5. Let us see the question number 5. Check whether 6 power n can end with the digit 0 for any natural number n. What is the question? Let us see once again. Check whether 6 power n can end with the digit 0. If you put any value for natural number n, in the place of n, if you put any natural number like 6 power 1, 6 power 2, 6 power 3 like that, is that result, that number will end with 0 or not? That is the question. So, for example, if 6 power n for any n value, for any n, okay, if were to be end with 0, what happens if it is to be end with 0? It should compulsory divisible by 5, because any number which has end digit as 0, it is compulsory divisible by 5. It should be divisible by 5. As the numbers which are divisible by 5 consists of end digits as 0 or 5, right? So if it is to be end with 0, it should be divisible by 5. That means what? It should contain the prime factorization. The prime factorization should contain the prime factorization of 6 power n should contain 5, right? Should contain 5. If it is to be divisible by 5 means compulsory the prime factorization will contain 5. But what happens? 6 power n, let us put it in the form of prime factorization. 6 I'll write as 2 into 3 power n. So which can be written as 2 power n into 3 power n. So what do you mean by this? That means the prime factorization of this 6 power n contains only 2's and 3's. It should contain only 2 power n and 3 power n. Means the whole prime factorization consists of only 2's and 3's. According to uniqueness of fundamental theorem of arithmetic, what it says? There are no other primes except the prime factorization of 6 power n is unique. Compulsory, anybody may try this. It will compulsory contains 2's and 3's only. It doesn't contain any other factor. That means it is not divisible by 5. It is not containing 5. It is not containing 5 and it is not divisible by 5. So only the prime factorization contains only 2's and 3's. That means 6 power n is not divisible by 5. So its prime factorization does not contain 5. And then you can say that there is no natural number for n, whatever takes the value here, it ends with the digit 0. There is, for any natural number n, 6 power n cannot end with 0. Okay, let us see question number 6 now. Now let us see the question number 6. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. So we need to prove that these two numbers are composite numbers. So what is meant by composite numbers? Let's recall first. Composite numbers are those which have more than 2 factors. So it is enough if we show that these numbers have more than 2 factors. If they have more than 2 factors, then we can say that they are composite numbers. So for that, let us take the first one. Let us prove that it has more than 2 factors. So this is the number, first term plus 13 to that. So instead of doing simplification completely, what we can do is, here you observe that 13 is a common term in both. 13 is common in both. So let us take 13 outside and write the remaining terms inside. 13 into 7 into 11. So that is the first term, and plus 13 is there. You think this 13 as 13 into 1, and so 13 if taken out, 1 is left over, so plus 1. So which we can further write as 13 into 77, this one, 7 into 11 plus 1, which gives you 13 times 78. So which is nothing but 1014. If you observe that this 1014, which is the answer of the whole expression what he has given, this is a multiple of these two numbers, because we got this by multiplying 13 into 78. So clearly we can say 13 and 78 are factors of 1014. So if 1014 has factors of these two numbers, other than these two, it also has 1 and itself, because for every number 1 and itself are also factors. So these are also factors of 1015. So what did you understand now? Basically, this 1014 has totally all this more than 2 factors. 4 factors are there obviously. So you can say that this has more than 2 factors. So 1014 or the given expression whatever is a composite number, right? So as it has more than 2 factors. So let us see the second one now. Similarly, 7 into 6 into 5 into 4 into 3 into 2 into 1. This is all whole one term plus 5. So this is an expression. Now let us see whether it is a composite number or not. Here also, if you observe carefully, 5 is common in both. So let us take 5 as common and write it as 7 into 6 into 4 into 3 into 2 into 1 plus 1. As you think 5 as 5 into 1. So if you take 5 as common, you get this. So totally you can write like this. Now 5 into, let us multiply the inner part. 5 into 1008. If you multiply all this, you will get 1008 plus 1, which gives you 5 into 1009. This is equal to 5045. Now you understand that 5045 is a multiple of these two numbers. That means 5 and 1009 are factors of 5045. Obviously, other than this, we have anyhow for every number 1 and itself are also the factors. So these two are also factors of 5000, same number 5045. So what did you understand now? 5045 has more than 2 factors. Other than 1 and itself, it has 2 more factors also. So while 5045 is also a composite number, as it has more than 2 factors, also a composite number, right? Now see, let's go to the question number 7 now. Now let us see the 7th question. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Try to understand the question again. Sonia is taking 18 minutes for every round. whereas Ravi takes for every round 12 minutes. Okay, so that means Sonia takes 18 minutes to drive one round, means she takes multiples of 18 to complete each next round. That means she takes 18 minutes for first round and 36 minutes, double of this, 36 minutes for the second round, and like that 54 minutes for the third round, and so on, 72 minutes, and so on, like that. For every round 18 will be added. These are the multiples of 18, which are the timings taken by Sonia for every round continuously. And now this is about Sonia. Now coming to Ravi. So Ravi takes every round, for every round 12 minutes. That means for first round he'll take 12 minutes, and for the second round he'll take 24 minutes, and for the third round he'll take 36 minutes, and so on, like that, 48. These are the multiples of 12. So Ravi takes multiples of 12 to complete each round, whereas Sonia takes multiples of 18 to complete each round. Okay, now when they'll meet again, if they start both together at the same place at the same point, and after completing the rounds, where they'll meet again at the same starting point. That means that happens when they have the same multiple, the very first multiple. They both meet again at the first or the first coming multiple of both 18 and 12. So that means we should find the least common multiple. So we should find what is LCM, least common multiple of 18 and 12. That means you need to find the, already we got the answer, that is 36. After 36 minutes they'll meet again. So that you can also find by your prime factorization method also. So we need to find LCM of 18 and 12. That means the first coming multiple of both 18 and 12. So that you can find like by prime factorization, 18 is equal to 2 into 3 into 3. 2 3s are 6, 6 3s are 18. Similarly, 12 we can write as 2 into 2 into 3. 2 2s 4, 4 3s 12. Now, what is the common multiple? So, how do you find common multiple? First of all, take the common number which is in both. So, 2 is common in both, and 3 is also common in both. So, first of all, let us take those two numbers, 2 and 3. And other than that, what are common also we should take for LCM. For HCF, this is enough. For HCF 2 and 3 only, but here it's not HCF, just I'm telling. So what you have to take for LCM, you need to take the extra numbers also. Let us continue. Into 3 into 2. So now the number is 2 3s are 6, 6 3s are 18, 18 2s are 36. So LCM is 36, which already we found here by finding the multiples method. This is finding by multiples method. This is by prime factorization method. Okay, so they both meet again after 36 minutes. Okay, so this is about all the sums in the exercise 1.2. Bye. Thank you.